Hello everyone. So let's begin lecture 11 on the topic for this lecture is auto transformers. This is again an interesting concept and there are actually practical uses and there are many transformers which are auto transformers. So what is an auto transformer? So auto transformer is a transformer with only one winding. Now normally we discuss transform with two windings. It is just transform with only one winding. Then how does it actually work? Because we had number of turns in the primary, number of turns in the secondary, then the turns ratio, all these things which you discussed in two winding transformer. How does it apply to one winding transformer? So the idea is like this: we just have one winding. So let's call this entire winding as A B. So and it has a core. This winding is wound across a core. So the where we get the terminals is I'll just take a point which is slightly below this and then I'll just take a tapping out of it. And this point let's call it C, and these two terminals are is my secondary terminals, and these two terminals I'll consider as my primary terminals. So then this will be a kind of a transformer. What does a transformer do? A transformer transforms the voltages. So whatever voltage is here, slightly lesser voltage will come here because the number of turns are less. So for example, if I consider total this entire winding, that is N1 as 1000 turns, and then this one I've just slightly reduced it, so maybe N2 is only 950 turns. So what is happening here is, am I counting these particular turns both under primary and secondary? Yes. So the same turn is in the primary side and the same turn is also counted in the secondary side because the voltage that comes is proportional to the number of turns here. So whatever voltage I apply here, the applied voltage. So let's say the applied voltage is V1 at the terminals. So that particular applied voltage, so this is just a AC voltage by the way. So this applied voltage will be distributed evenly across all the turns, and therefore if I'm only taking 950 turns as secondary, so this will be slightly less. So basically it will be 95% of the applied voltage here. So V2, so if you don't consider the drop and all the other practical aspects, if you consider it as an ideal auto transformer, so V2 will be 0.95 or 95% of V1 because slightly less number of turns is there, 1000 versus 950 turns. Let me also mark the currents. So this current denoted by I1, this current denoted by I2. Therefore, by applying Kirchhoff's current law at this point C, I can find what is a current here. So that current, so I'm considering the direction as current going from this point to this point. So therefore, the current will be I2 vector minus I1 vector. So this is the current. So this current, let's call it as IC or I naught or what. IC, let's call it. It's a common current, let's call it. So far, so good. So if you connect a load, so for the time being, this is a no load. So if there is no load, then what is I2 dash? So I2 bar, this is nothing but 0. So therefore, this current also will be 0, except this current will be, as we discussed, there will be some magnetizing component and then the core will get magnetized and all these things. So and also there is equivalent resistance working component and all that. So this I1 will be nothing but I naught. And as always, as for the other regular transformer, this I naught will be like 2 to 3% of the total current. So we can actually ignore it for the time being because I want to explain the working principle of it now. Okay, so now what do we have? So I have explained that this is a auto transformer and just like any transformer, it can do transformation of voltage. And here, slightly I'm reducing the voltage. Now, but why to do like this? Why not have a regular two winding transformer? So there are advantages. So the advantages are, first one is less amount of copper. So the windings, the same these turns, 950 turns, are shared across both. So because of the sharing of copper, so less amount of copper is needed, less weight, and as a result, less cost. So it is suitable when N2 by N1 is close to 1. So the magnitude of N2 by N1 is uh, near to 1. Okay, so now I had said less copper, less weight, and less cost. So less cost is obvious. If I show this above two, it is easy to say that it is less cost because the material itself is being used is less. So now the next part is how does it work, and then what is the justification? Why it amounts to less copper, less weight, and so on is what we are going to discuss. Now let's analyze this a little bit further. So we know that the transformer is transforming the voltages. So therefore, the quantity V2 by V1 is nothing but your transformation ratio, and that will be, for the currents it will be like reverse, I1 by I2, because if the voltage is reducing, the current will increase to compensate the same voltage, like that is to compensate the ampere turns. So this is N2 by N1, and this quantity we are defining it as K. So this is same as the theory that you uh, seen for the two winding transformer. Transformer ratio K is considered as V2 by V1 or N2 by N1 and then I1 by I2. So now when we apply for this particular problem, so then so we get step down transformer. We get voltages because the number of turns N2 is slightly less than N1. So in this case, N2 is 950 and N1 is 1000. So therefore, the value of K will become 0.95. So now let's see how it will help. So the way it will help is it is doing the regular job compared to the two winding transformer. How it will help. So for that, I need to write something like this. What is the weight of the copper in a transformer? So weight of the copper in a transformer is proportional to the volume of the copper. So because the density of the copper is kind of fixed for a given material, so the more volume of copper you are using in a transformer, the more weight it is. And the volume of copper is proportional to the length of the total copper used and cross section area. So volume is nothing but length into area. It's a wire, so it has a cross section area and it has a length. And the length is proportional to the number of turns. And the area of cross section is proportional to the current. Because if you want to carry more current, you will have to use a larger cross section area. Otherwise, the resistance will be more and heating will be more and this kind of problems. So typically, the current capacity is proportional to the current carrying capacity of a wire is proportional to the area of cross section of the wire. So therefore, so you notice N into I is nothing but ampere turns. Ampere turns of the transformer. So therefore, whenever you are talking about weight of copper used in a transformer, that is proportional to the ampere turns in the transformer. So therefore, let's define WC and let's say WA, not WC, and W2. So WA is weight of auto transformer. weight of copper of auto transformer. And then this is weight of copper for a regular transformer, two winding transformer. I want to compare these two in such a way that both of them are having same, like N1, N2, and then the I1, I2 are same. So consider two transformers. So one transformer is auto transformer, one is auto transformer, and the other is regular two winding transformer. So now both of them having same N1, N2, I1, I2 are same for both. But then for the second one, we use more copper, and the first one we use less copper. That's what I want to say. So WA. So if you look at WA proportional to ampere turns. So what are the ampere turns? Now look at this diagram. So current I1 is flowing in this part of the A to C part of the transformer. So how many turns are there in A to C? That is nothing but N2, sorry, N1 minus N2. And so here the number of turns is N1 minus N2. And here the number of turns is N2 and the total turns is N1. So therefore in the part of the winding N1 minus N2 current is I1. And in the part of the winding the remaining N2 turns the current is I2 minus I1 as you can see here. So let me write that. So the total ampere turns for auto transformer is proportional to, like weight of auto transformer is proportional to ampere turns. So N1 minus N2 multiplied by I1 plus I2 minus I1 multiplied by N2. So this is what is the quantity proportional to which is the weight of copper. Now these are all current I1, I2 and all are complex numbers. So what to do with that? So if you just analyze it a little bit further, you notice that this I1 and I2, although it's a vector difference, actually these two currents are kind of in the same direction, that is I1 and I2. If you just take this to the top, you'll see that I1 actually equal to I2. If this tapping is taken at point A, then slightly moving down, they're still like kind of magnitude is different, but the direction is same or phase is same for these two. So therefore, I can actually, instead of taking a vector difference, I can actually take the normal difference, I2 minus I1. And why I2 minus I1 is taken, why not I1 minus I2, is because this direction, of course. So if this direction is upwards, then according to KCL, it is I2 minus. But then why this direction is being chosen is that we know that I2 will be positive and I2 will be more than I1, so that this IC will be positive. So that is what is the concept here. Because you are going for step down, the voltage is stepping down, but the current will step up. Therefore, I2 will be magnitude wise more than I1. So therefore, this quantity will become positive. That's why this direction has been chosen for the step down transformer. And this will be positive. But this is true only when we are talking about a step down transformer. We'll come back to that point here. So I know that this quantity is positive. So, and therefore I can just write it N1 I1 minus N2 I1 plus, so and I can also get rid of the vector notation because uh, these two are almost in phase, so I can just ignore the angle because I can take only the magnitude I1 N2. And if I further do this, so N1 I1 plus this term, sorry, N2 I2. So this term and this term both are same. So I get minus 2 N2 I1. So this is weight of auto transformer. So what about weight of regular transformer? Weight of two winding transformer. That is proportional to N1 I1 plus N2 I2. This is like assuming there is a regular two winding transformer. This is a total ampere turns on primary and secondary side. So therefore now if I take the ratio of these two, weight of auto transformer divided by weight of two winding transformer, this is W2. This is weight of the copper of that. Okay. So I just divide these two. So I'll get, you notice this term is 1. So this is 1 minus 2 into N2 I1 by N1 I1 plus N2 I2. So now I want to eliminate and then simplify this. So first what I'll do is I divide the numerator by N1 and I divide the denominator by N1. So by doing this, what I'll get is 1 minus 2k I1 divided by, this is I1 plus this term. This is N2 by N1 into I2. So what is N2 by N1 into I2? This whole thing. So if I go up, so N2 by N1 multiplied by I2. If I take the I2 on the other side, it will be nothing but I1. So I1 is N2 by N1 into I2. So this is just what we get from it. So using that relation, I'll just substitute it here. So here this whole thing is nothing but I1. This whole thing is also I1. And therefore, so I get 1 minus 2k I1 divided by 2I1. So 2I1 will cancel. Finally, I'll get 1 minus k. So this is now weight of auto transformer is nothing but weight of two winding transformer multiplied by 1 minus k. So that is nothing but W2 minus W2 into k. Now what is saving? Saving of copper. Saving of copper is nothing but W2 minus WA. Weight of two winding transformer minus weight of auto transformer. If I do this, then I'll get the saving in the copper. So from this above, if I just bring this WA to the other side and this term to the other side, so I'll get W, so it's nothing but K into W2. So this is very important uh, point. So the saving is proportional to the K. So therefore, that's why when I draw the auto transformer like this, so if I take a tapping very low, so let's say this is 200 turns and this is total is 1000 turns, then this is still an auto transformer. This is still tapped down. Everything is fine, but then saving in copper will be only of the order of zero point 0.2 of W2. So only 20% you get the saving. So when you get the maximum saving is when you take the tapping as close to the unity as possible. That is as close to 1 as possible. So because the saving is proportional to K. So therefore auto transformer is suitable when K is less than or equal to 1 and close to 1. Let's discuss the trivial situation where K equal to 1. That means what you are doing is just having a coil and a core in between, and then here you apply V1 and V2, and here I1 will flow and here I2 will flow. So this is actually, if you ignore the magnetizing component of current I0, if you ignore that, then no current is flowing like this. So therefore there is no need for setting up a transformer. So there is 100% saving in the copper. I1 will be equal to I2, V1 will be equal to V2, and it's just like a set of wires. This is a trivial extreme case. Whereas as you start decreasing K is 0.95, K is 0.9, 0.8, like that you start taking tapping here, you will get the benefit. So auto transformer is used when you want slight step down. But what about step up? Can K be more than 1? That we'll discuss next. Let's look at a step up auto transformer in which we are trying to increase the voltage. So what is the benefit? So again, you have, this is the single winding, and there's a core also. So the terminals that I take from this side are the secondary terminals. So this is V2 and this current is I2. And what I'll do is, instead of taking it from here slightly below, I'll take the tapping and then I connect out to this. So this is V1 terminal voltage and this current is I1. So this is the primary side and this is the secondary side. And I can now connect a load here. So this is a load. And the moment I close the switch and the moment I provide my supply V1, then this particular auto transformer will start working such that it is increasing the voltage. So V2 will be more. So because here you see, notice that the total number of turns in the secondary winding is N2, and on the primary winding only there will be a part of it. So this winding, if you count this as N1, then we have N1 turns from here to here. So and N2 is turns from here to here. And how many turns are in this part? So this part will be N2 minus N1, like this. So this turns N2 minus N1, this part. So if I again denote A, B and C, so like this. And what is the relation between the voltages and currents? So it's exactly the same. K is defined as the transformer ratio N2 by N1, which will be equal to V2 by V1, which will be equal to I1 by I2. Now I2 is determined by the load, and then once I2 is determined, all other I1 and N1 and V1 and all are determined. So I2 is determined by the load and V1 is determined by the supply. Okay, now let's see whether there is any copper saving in this. So what is the weight of copper in the auto transformer? So this is WA. I'll just do the same analysis. So you see N2 minus, I'll have to now mark the current. So now it's very important to mark the current properly. See, because this is step up, the magnitude of I2 will be less than the magnitude of I1. Because the voltage is less, the current will be more. And because the voltage is more, here the current will be less. So magnitude wise, I1 will be greater than I2. So therefore, now look at this current going like this. And then if I define the current going downwards here in this winding, let's define this current as IC. So the IC current going downwards will be I1 minus I2. This is Kirchhoff's current law applied at this point. IC current is going downwards, so outgoing current is equal to the incoming current minus again another outgoing current. So like this. And these are actually vectors, but then since they will be more or less in phase, I can ignore. I can just subtract the magnitudes directly to get the IC current in this part of winding. So therefore, what are the ampere turns? So here the current is I2. So I2 multiplied by N2 minus N1, and then this current I1 minus I2 multiplied by N1 is the total ampere turns. So N1 multiplied by I1 minus I2, and then we have I2 multiplied by N2 minus N1. Now, why have we taken the downward direction? We have taken downward direction because we know that this has to be positive and we know that I1 will be greater than I2. So therefore, the current will go downwards. Earlier in the case of step up, step down transformer, we had taken the direction in the reverse way. So, but then this consideration we have to give. And if I simplify this, this will be N1 I1 plus N2 I2. So this is one term, N1 into I1, N2 into I2. Then the other term will be I2 into N1 and I2 into N1. So minus 2 I2 N1. So this is weight of auto transformer, first step up, and weight of copper. So weight of weight of copper for a two winding transformer, as you know, it will be N1 plus N2 I2. So this one. So now if I divide these two, I'll get the ratio. So that is WA by W2 is, so this whole thing is dividing. So therefore here it will be 1 and then here it will be minus 2 I2 N1 divided by, I'm sorry, N1 I1 plus N2 I2. Now if I divide this by N2, if I divide this by N2, if I divide this by N2, so this will be 1, and what is N1 by N2? That will be nothing but 1 by K. So this is nothing but 1 by K. This is also 1 by K. Now whereas N1 I1 by N2 is nothing but I2. So overall what you get is 1 minus 2 I2 divided by I2 plus I2, and of course here it is 1 by K, 1 divided by K. So this I2, this is nothing but 1 minus 2I2 by 2I2 into 1 by K. So this whole thing will cancel. So therefore 1 minus 1 by K is the final WA by WC. So therefore if I want WA, that will be this is W2. W2 minus W2 divided by K. And therefore if you want saving in copper, that will be W2 minus WA. So that will be nothing but W2 by K, where we are discussing step-up transformer. So K will be greater than or equal to 1. Now if K equal to 1, then the entire saving will be entire W2, but then as K value keeps on increasing, that means as you go for more and more step up, the benefit will be lost, the saving will be less. So therefore saving will be better if K is slightly more than 1, slightly above 1 for step up transformer, of course, and if K is slightly below 1 for step down transformer. So basically for auto transformer, saving of copper is better if magnitude of K is close to 1. So therefore we don't find people using auto transformer for, let's say, major generators, that is, let's say 13 kV is generated and I want to step up to 132 kV. So almost a factor of 10. So for 1 is to 10, it is better to have a two winding transformer. You will have electrical isolation and there are other benefits that way. Whereas if there is a slight variation in the voltages and the transformer ratio is close to 1, then we prefer auto transformer. So based on this, let's work out some numerical examples. So I had shown you two cases: step down auto transformer, step up auto transformer, and based on that, we'll try to gain better understanding. Let's begin by looking at this example. This is example 37 and about auto transformer. So you might consider pausing the video now, look at the question, try to attempt solution yourself, and you can later compare your answer with my answer. So I'll get started here. So what I have is the primary and secondary voltage of auto transformer are 1000 volts and 950 volts. So therefore, it is a step down transformer. So let me begin by drawing that step down transformer. So this is step down transformer. So this is 1000 volts and 950 volts. So there's nothing given about voltage drops or anything. So I'll consider the terminal voltage as same as the induced EMF. So this is 1000 volts and this is 950 volts. So when I say plus minus, it's actually alternating current, it goes without saying, just to show where is the positive side. Alright, the secondary is supplying current of 100 amperes. So the secondary is supplying current of 100 amperes. So I2 is equal to 100 amperes. At a load, to a load at a unity power factor, calculate the currents in all parts of the auto transformer and the percentage saving in copper for the auto transformer. Alright, so if this current is 100 amperes, what will be the current here, I1? So as I said, the total output power, if you see, so if just think of this as a box, the power coming out of the box is 100 into 950. So actually the power output is nothing but 95 kilowatts. So therefore the power input will also be 95 kilowatts, and therefore already the voltage is 1000, so therefore the current will be 95 kilowatts divided by 1000, so it will be 95 amperes. So that is how we can just estimate based on the powers. Also, you can blindly use the equation, that is something like this, that is N1 by N2 equal to V2 by V1 equal to I'm sorry, this is just N2 by N1 equal to V2 by V1, which is equal to I1 by I2. So from all this, I can calculate what is I1. That is V2 into I2 by V1. So that is 950 into 100 divided by 1000. So I'll get 95 amperes for this. So if this current is 95 amperes and this current is 100 amperes, the remaining 5 amperes must be coming from the remaining turns of this particular transformer. So what is the saving in copper? So saving in copper will be, of course, nothing but K, which will be nothing but 0.95. This is nothing but 95% saving in the copper. So this is the current distribution. All right. So now let's continue and let's look at one more problem. So this is example 38. So you notice that everything is exactly same, only difference is here that the primary and secondary voltages are reversed. So this is now a step up transformer. Earlier we studied step down transformer. So let's again draw the diagram for that. This time this voltage is 1000 volts, and here I'm sorry, this voltage is only 950 volts, and at the output I have 1000 volts, and this current is given to be 100 amperes. So what will be this current? So of course, because the voltage is less, the current will be more. So we can actually calculate that. So what is I1? So we'll use the same formula. So I1 by I2. So this will be N2 I2 by N1. So that will be, so how many turns are there in the total secondary? So I have all the turns, that is, I can also change it by V2 I2 by V1. So V2 is 1000 and I2 is 100 and divided by 950. So here we require a calculator. If I'm just opening my calculator. So 1000 multiplied by 100 divided by 950. So I'm getting 105.26 amperes. So this is 105.26 amperes. So this is it. And what about the saving in copper? What about this current before that? So this is I1. What about the current in this part of the circuit? So will the current be up or down? It will be down because 105 amperes more current is coming. So the remaining 5.26 amperes will be going down like this, and then it will go back here 105.26, and here 100 amperes will come like this. All right, savings in copper. Savings in copper will be again, I think it will be 1 by K. So what is K here? So K is N2 by N1. So that is 1000 by 950. So therefore, I think it's basically the same thing, I think. And then this will be again inverse. So if I just invert this, so I'll get 95%. So saving in copper is exactly same, 95%. So I hope with these two problems, 37 and 38, you kind of understood how the transformer, auto transformer works. We'll solve more problems. So let's look at another problem. This is example 39. So what is given? An auto transformer supplies a load of 4 kilowatt at 110 volts at unity power factor. So if the primary voltage is V, so therefore the power P2 is 4 kilowatts, and at UPF, unity power factor, and V2 is 110 volts. All right. If the applied primary voltage is 150, so V1 is 150 volts. Calculate the power transferred to the load inductively and conductively. So the power is transferring from primary side to the secondary side. So some part is going inductively and the other part is going conductively. So how do you find out how do you calculate for this? So there is, it can be shown that the inductive component or inductive fraction of power is nothing but 1 minus K multiplied by P1, the input power. So let's calculate that. So here what is K? So K is V2 by V1, which is nothing but 110 by 150. So how much is that? 110 divided by 150. So 73.33%. So 0.733. So therefore the amount of power transferred inductively. So P1 will be equal to P2. Ignoring losses. So just ignoring losses. Input power will be equal to output power because just a transformer is only transferring power from one circuit to the other circuit, ignoring losses, and no data is given to calculate losses. So therefore, I'll get 1 minus 0.733 multiplied by P1, that is 4 kilowatt. So let me just multiply by 4 this one. This is 2.933. This is actually conductive fraction of power is 2.93 kilowatts, and therefore the remaining part will be inductive component. So if I just minus 4 from this, so I'll get 1.06 or 1.07 kilowatts. So out of the total 4 kilowatts which is delivered to the load, 2.93 is conductively delivered, and that is through actual flow, the electrically delivered, and 1.07 is to the inductively delivered, that is through the transformer action. So basically what we are trying to do is, because we are doing less of a transformer action, that is induction, so the saving is there in the copper. All right, so let's continue in the next problem. The core of an auto transformer can support a maximum flux density of 1.2 Tesla. So therefore, maximum flux density B max is 1.2 Tesla and has a cross section area of 200 centimeters square. So cross section area is 200 centimeters square, which is nothing but 200 into 10 power minus 4 meters square. So I converted into meters. So Tesla is nothing but Webers per meter square. So everything is in the same units. The auto transformer is operating at frequency of 50 hertz. So F is 50 hertz given to you. So it is required to have the voltage ratio of 8200 and by 700 determine the number of turns in the winding and tapping position for the secondary. So from this data given, so we know that induced EMF equation is 4.44 into F into Bm into A into N, number of turns. So therefore if I transfer that N here, so then I'll get, so this is nothing but EMF per turn. So for one turn, how much EMF I get it. So that is what we are going to calculate. All the data is given. So 50 into 1.2 into 200 into 10 power minus 4. So 0 and 2 more zeros, and then this will be 10 power minus 1. So I'll just make it 0.5. So I have 4.44 multiplied by 0.5 multiplied by 1.2. So I'm getting 2.664 volts. Let me just cross check it again. 4.44 multiplied by 0.5 multiplied by 1.2. Yeah, 2.664. So 2.664 volts per turn I get it. So therefore to get the total of 8200 volts, so therefore total N or N1 will be 8200 volts is my required voltage divided by 2.664. So 8200 divided by 2.664. So I'm getting 3078 turns. 3078 turns. So this many turns I have to do on the winding. Now where do you get the secondary, that is N2? So this is 7000 divided by 2.664. This is where we do the tapping. So that is 7000 divided by 2.664. So I'm getting 2627.6. So I'll round it off to 2628. So 2628 turns. So that means if I have the total winding, so this total turns is 3078 turns. So from bottom I'll just take 2628 turns and I take the tapping at that point. So how many turns are remaining here? I just have to take the difference of these two. So minus 3078. So about 450 turns. So about 450 turns if I just leave out, the remaining 2628 turns if I just take a tapping outside. So here I can expect to get 7000 volts if I give 8200 volts at the input. So this is what is the solution for this problem. Okay, so let's now look at this problem, that is example 41, where the currents in the auto transformer discussed in example 37 are shown below. So this is just the same diagram that we discussed sometime back in the example 37. So this one. So now what I have done is I've just copied the same figure, and in this problem 41, our objective is to determine the KVA rating of the winding used in the auto transformer. So how do you determine the KVA rating of the winding? So it's nothing but you take the winding and multiply its voltage and current. So if you look at the winding here, so this part of the winding, so if I just say A and this end is B and this end is C, so for part AC, so what is the voltage? So the voltage will be total is 1000 volts and 950 volts. It's only 50 volts. But what is the current? The current transferred by this part AC is actually 95 amperes that you can see. So therefore, for the part AC, the KVA rating will be 50 multiplied by 95. So let's quickly do that calculation. I'll just bring up the calculator. So 50 multiplied by 95. So I'm getting 4750. So that is 4750 volt amperes. So this is for the part A to C. Now for the part C to B, for part C to B, what do I require? So here voltage is actually 950 volts and current is actually 5 amperes. So you notice that because this only 5 amperes is there, I can use a wire with very thin cross section area. I don't require a very thick wire because I am to only carry 5 amperes compared to this part. So therefore A to B is not a one continuous wire. Actually two different varying thickness can be used uh, to save the copper actually. So and we have already considered that because we had when we are calculating the copper weight saving, we had already considered that factor. That is, the weight is proportional to the current. So ampere turns basically. So therefore, that part is already considered. So anyway, so what is the volt amperes for this part? So that is 950 volts into 5 amperes. I get again 4750 volt amperes. So the total volt amperes, if you see, it will be 0, 0 and then 5 and then 9. So this is 9500 volt amperes, or I could say 9.5 kilovolt amperes. So this is what, this is the rating of winding, of the single winding of auto transformer. But then look at the total output that the auto transformer is generating. So if you look at the total output power, what is output power? 950 volts into 100 amperes. So that is actually 95 kilowatts. Or if you consider unity power factor, it is 95 kVA. So to generate an output of 95 kVA, 9.5 kVA rating of winding of auto transformer is sufficient. So that's interesting. Compare it with the two winding transformer. If you had two winding transformer, then if this was 950 volts and 100 amperes, so this winding itself will be 95 kVA rating because it is handling 950 volts at 100 amperes. What about the other winding? This is 1000 volts handling 95 amperes. So this is again 95 kVA. So each winding is 95 kVA in the case of a two winding transformer rating. Whereas with just one winding of 9.5 kVA rating itself, I am able to do the voltage transformation from 100 volts to 1000 volts to 950 volts. So I hope you find this interesting. This is a benefit of using a auto transformer. We get a boost in the KVA rating also. So all of this is because we are not converting the entire 100% of the input power inductively. A part of it we are only, maybe like in this example, 5% is conducted inductively and the remaining 95% is conducted conductively, is transferred from primary to secondary conductively. So there is the benefit that we are having by using this auto transformer. So here is another interesting problem. This is on three-phase auto transformer. So let's look at it. You can again try this. I think there is a problem here. So this is 440 by 500 volts. There is a typo. All right. So let's look at the problem. Find the values of currents flowing in various branches of a three-phase star-connected auto transformer loaded with 400 kilowatt at 0.8 power factor lag, having a transformation ratio of, so you notice this is a step-up transformer. Neglect any voltage drops, magnetizing currents and losses. So first of all, let's draw a three-phase star connected auto transformer. So to draw the auto transformer, so this is one winding. So ultimately it is a star connected winding. So each one represents one phase. So now if I just take it outside like this, these terminals, then these are my secondary terminals, and therefore the line voltage here, so line voltage between any of these is actually 500 volts. So this is the secondary side. And there is a three-phase load connected here. This is just connected like this. And this load is 400 kilowatts at 0.8 power factor. Now what is there on the primary side? Because it's just 440 volt less than this 500, so I have to take a tapping somewhere in the middle like this. So this many turns will account for 440 volts, and the total turns will account for 500 volts. So in that ratio you have to take a tapping. So by the way, this is 500 volts line voltage. So therefore this voltage will be 500 by square root of 3, and this voltage will be 440 by square root of 3. But then by the time I take this terminal out, and then here also I take a tap, and here also I take a tap. So this voltage will again come out to be line voltage, that will be 440 volts. So this is how it looks like. Now let us mark the currents. So the currents are, this is one current, let's call this current as I2 line current. And luckily all line currents and phase currents are same in this. So whereas this current is I1 line current, that is primary line current. And let's mark the current which is going down as I1 minus I2, or let's call this I3 or IC, common current or whatever. So now my objective now, or our objective, is to determine what is the value of I2, I1 and IC. So let's first find out I2. So what is I2? A line current. How do you find? So we know that output power is nothing but root 3 VL IL cos of phi. So therefore from this I'll find what is I2 line. So I2 line will be, output power is 400 kilowatts. Let me just verify that. 400 kilowatt, yes. So divided by root 3 VL cos phi. So root 3 into line voltage is 500 volts and power factor is 0.8. So this will give me the answer. So this is kilo also, just make a note of it. So I'll just strike off these zeros. 5 into 0.8 is actually 4. So this also I can strike off. So finally it is 1000 by root 3. So how much is that? So let me just go to calculator. So 1000 divided by square root of 3 is equal to 577.35 amperes. So I'll just round it off to 577 amperes. So where is this current flowing? So this current is flowing here at this point. So here it is 577 amperes. So here also. So now what about the input current? So for that I can again, because there are no losses in the transformer, output is 400 kilowatt. So input also can be assumed to be 400 kilowatts. So since we are neglecting the losses. So how to calculate I1? So I1 is nothing but 400 kilowatt is the output, whereas just the voltage is different now, 440 volts into 0.8. So this is the difference. So let me do the calculation now. So I'll just clear everything. So 400,000 divided by 3 square root multiplied by 440 multiplied by 0.8, closing the brackets, and is equal to 656 amperes. So of course we expect a higher value because this is low voltage side, the current will be higher, 656 amperes. Now the remaining current will be IC. So this will be nothing but I1 minus I2. So strictly speaking, it's a vector difference, but then in this auto transformer, these two are already in phase, so we can just subtract them directly. So IC, the current in the common part of the network, so will be 656 minus 577. So that will be minus 577. That is 79 amperes. So 79 amperes is flowing in this part. So here it is 79 amperes. So if I mark the currents, so this is 79 amperes, this is 79 amperes. All these three 79 amperes will meet here and they will cancel out each other because they are all 120 degrees apart. And then here the current is 656, here the current is 656, here the current is 577. So this is the final solution of the problem. So to basically conclude this session, today we had in this video we had seen the auto transformer, what is the working principle of the auto transformer, how the auto transformer is constructed. Just we are using only one winding and taking tappings for primary and secondary, and the transformation of the power is both inductively and conductively. So therefore we are getting some saving in the weight. So weight of copper we are getting saving, and that saving we found out to be proportional to 1 minus k for a step down transformer, and then 1 minus 1 by k for a step up transformer. And on this concept we had solved some problems. So I hope you had learned something in this video. In the next video we are going to, on the next lecture we are going to see, if I convert a two winding transformer into a auto transformer by just changing the connections, what is going to happen. So that's what we'll see in the next lecture. Thank you. So if you like my videos, please do press the like button and please do subscribe. Thank you.